When we first introduced hypothesis testing in Unit 1, we likened it to a court case. And just like court cases, hypothesis tests are not flawless. In the court system, innocent people sometimes are wrongly convicted, and sometimes the guilty walk free. Similarly, we can make a wrong decision in statistical hypothesis tests as well. The difference, though, is that we have the tools necessary to quantify how often we make errors in statistics. So in this video, we're going to first introduce type 1 and type 2 errors, and we're also going to discuss a little bit how we can balance these error rates. Just to give you a sneak peek, the likelihood of making a type 1 error and likelihood of making a type 2 error are actually inversely proportional. So it's actually not all that easy to keep both of those error rates down. So sometimes we have to choose, and we're going to talk about how do we choose between which one we are okay with being a little higher versus which one we really want to minimize as much as possible. Here's a 2x2 table that basically tells us what the true state of the hypotheses are, and remember that we usually don't know whether the null hypothesis or the alternative hypothesis is true, but we make a decision regardless based on the evidence that we collect or in the statistical significance of that evidence. If the null hypothesis is indeed true and you fail to reject it, you've done the right thing. There's absolutely no reason to worry. Similarly, if the alternative hypothesis is true and you reject the null hypothesis in favor of the alternative, once again, you've done the right thing. But how about the other two cells? A type 1 error is rejecting the null hypothesis when the null hypothesis is actually true. So in other words, rejecting the null hypothesis when you should not have. A type 2 error is failing to reject the null hypothesis when the alternative is true. In other words, it's failing to reject the null hypothesis when you shouldn't have. We almost never know if the null or the alternative is true, but we need to consider all possibilities. So if we again think of a hypothesis test as a criminal trial, then it makes sense to frame the verdict in terms of the null and the alternative hypotheses. The null hypothesis says that the defendant is innocent. Remember, usually it's innocent until proven guilty, at least in the US, so it makes sense that the status quo, the null hypothesis, it says that the defendant is innocent. The alternative says that the defendant is guilty. So let's take a look at these two questions. Which type of error is being committed in the following circumstances? Declaring the defendant innocent when they are actually guilty. So in this case, we are saying that the defendant is innocent, however, they are actually guilty. This means that we are failing to reject the null hypothesis when the alternative is actually true. Indeed, that is a type 2 error. And the converse of that is declaring the defendant guilty when they're actually innocent. So in this case, we have rejected the null hypothesis in favor of the alternative when the null was true, and that is the definition of a type 1 error. One question we might then ask is, which error is the worst to make? A type 2 error where we declare the defendant innocent when they're actually guilty, or a type 1 error where we declare the defendant guilty when they're actually innocent? One might consider this a subjective question. However, usually I think there's a consensus around a quote from William Blackstone: "Better that 10 guilty persons escape than 1 innocent suffer." So if you agree with this and you're setting up your hypothesis testing scheme, then you want to think about which error rate should I be minimizing so that I don't accidentally make suffer 1 innocent person, even if it means that a few of the guilty ones might walk free. So in that case, we want to make sure that we want to minimize the rate of the type 1 error where we would be declaring a defendant guilty when they're actually innocent. If you do not agree with this statement and you think that a type 2 error is a worst offense, then in your case, you would want to be minimizing the type 2 error rate. Let's talk a little bit about the type 1 error rate. As a general rule, we reject the null hypothesis when the p-value is less than 0.05. In other words, we set our significance level, our alpha, to 0.05. This means that for those cases where the null hypothesis is actually true, we do not want to incorrectly reject it more than 5% of those times. In other words, when using a 5% significance level, there is about a 5% chance of making a type 1 error if the null hypothesis is true. We can simplify this to read as the probability of a type 1 error, given that the null hypothesis is true, is simply equal to the significance level that you set forth. This is why we prefer small values of alpha, because if we were to increase alpha, that might sound good because that would allow us to reject our null hypothesis more often, which is usually what we're trying to do. However, we would also be inflating our type 1 error rate. So increasing alpha increases the type 1 error rate, and that's why we like to keep it as small as possible. So how do we choose our alpha? That's actually a balancing act. If type 1 error is dangerous or especially costly, we might want to choose a small significance level, something even smaller than the 5% we're used to working with. The goal here is that we want to be very cautious about rejecting the null hypothesis, so we demand very strong evidence favoring the alternative before we would do so. If, on the other hand, the type 2 error is relatively more dangerous or much more costly, then we want to choose a higher significance level, because increasing our significance level will in turn have the effect of decreasing our type 2 error rate. The goal in this case would be that we want to be cautious about failing to reject the null hypothesis when the null is actually false. Let's take a look back at our truth versus decision table. A type 1 error, we said, is rejecting the null hypothesis when you shouldn't have, and the probability of doing so is alpha, our significance level. The type 2 error is failing to reject the null hypothesis when you should have, and the probability of doing so is labeled beta. This is not something we get to set ahead of time, and the calculation of beta is actually not that trivial. The power of a test is a positive thing, instead of an error where we have labeled this a positive word. This is the probability of correctly rejecting the null hypothesis, and the probability of doing so is 1 minus beta. If the alternative hypothesis is true, there are one of two things you can do. You might commit a type 2 error, and the probability of doing so is beta, or you might correctly reject the null hypothesis in favor of the alternative, and the probability of that then is going to be the complement of beta, 1 minus beta, and that's what we call our power. Our goal in general in hypothesis testing is to keep both alpha and beta low at the same time. But we know that as we push one down, the other is going to shoot up. So we usually want to find a delicate balance between these two probabilities. And let's wrap up our discussion by talking about the type 2 error rate. If the alternative hypothesis is actually true, what is the chance that we make a type 2 error? In other words, what is the chance that we fail to reject the null hypothesis even when we should reject it? The answer to this is not obvious. If the true population average is very close to the null value, it will be very difficult to detect a difference and to reject the null hypothesis. In other words, if the true population average is very different from the null value, it will be much easier to detect a difference. Clearly then, beta, the probability of making a type 2 error, depends on our effect size. And effect size is defined as the difference between the point estimate and the null value.